if we were given a quadratic equation in vertex form and asked to make a graph from that, well, we're quite comfortable with this at this point. We use our knowledge of our various transformations in order, and we're golden. But what if we turn things around and need to go the other way, using multiple transformations again? That is, given a graph, we need to determine the equation. Well, let's just look at that. In this tutorial, we'll discuss this type of question, and we'll do so by working through an example. Here's a graph, and we're to determine the equation that represents this same relationship. Let's start with our quadratic equation in vertex form, this layout, the A, B, and C. Now, if you choose to use the layout with the negative h and k, that'll work perfectly fine too. Feel free. Now, a good place to start is to determine the B and C. And we do that by locating the vertex on our graph, right here at 3, -2. So, the B, the horizontal shift would be, well, we've shifted right by 3, so we know that our B would have to be -3. And so let's look at the vertical shift, C. Well, we've shifted down by 2, so C would have to be -2. So at this point, we have an equation that looks like this. Y equals, well, we still don't know what A is, so we'll leave that, x minus 3 squared minus 2. So now we can work on the value of A. The first part is pretty easy. Is A positive or negative? Well, if it's U-shaped, then it's positive. If it's an N-shape, then negative. So this one is clearly positive. Okay, now positive what? Is it a positive 1 or is it some other positive number? To determine this, we think back to our most basic quadratic, y equals x squared. In this basic case, the A is 1, meaning that if we go over 1 to the right from the vertex, we go up 1 as well. So what does our graph do? If we go over 1, we see that we go up, not 1, but 2. So this tells us that we have a vertical expansion by 2. So we can plug that into our equation for A, and we get y equals 2, x minus 3 squared minus 2. And we're done. Now, are there other ways to put together an equation based on a quadratic graph? Well, you bet. Given that, this is the most common way, probably because it's easiest in most cases. So to review, we have two common ways of showing a quadratic relationship, an equation and a graph. And to this point, we focus on translating a given equation to a graph. But in this tutorial, we went the other direction, going from graph to equation. And to do so, we effectively reversed our steps. Going from the equation to graph, we learned that we need to do reflections and/or expansions and compressions, and then deal with the translations. Whereas going from graph to equation, it's easiest to look at the translations first, and then deal with the reflections and/or expansions and compressions. Thus, our first step was to identify the vertex on our graph, and use that to determine A and B, the translations. Whether we do reflections or expansions and compressions next, well, that's up to you. But many find it easiest to get the reflection out of the way, as it's really easy to determine. Is it positive or negative? Is the graph a U or an N? And from there, we look into the expansion and compression. So we find another point close to the vertex, maybe one right if possible. But you may end up using different point, maybe 2 right or 3 right from the vertex, looking for a nice intersection point on the grid. How does it compare to the basic quadratic relationship? That is, y equals x squared. Does our corresponding y value relative to the vertex match the basic quadratic? That is, 1 over, 1 up, or 2 over, 4 up, or 3 over and 9 up? Does our corresponding y value relative to the vertex match any of these? If so, then A is 1. If not, then we can use that to determine a factor. In our example, from the vertex, when we moved 1 right, we moved, well, not 1 up, but 2 up. So that tells us that A is 2 over 1, or 2. And a quick hint for success in these types of questions, you can always check yourself. Just take some points from your graph, plug them into your equation. Do they work?